Hi, welcome back. In this lecture, I want to continue talking about the Python multiprocessing module. In particular, I want to introduce the concepts of a pool and the operation on the pool of the task. So why do we want to use pools? Well, the problem with the multiprocessing.process object is that we need to manually create and manage process. And this is often a tedious part of the programming part. In particular, we need to start, spawn the processes and join them. And we do that individually. We have a loop to do that individually to each process. This process might become complicated and complex for tasks that require applying a function to many data points. So the solution for this kind of task is to use the multiprocessing.Pool. The usage of pools automates the process of creation and management of processes. It simplifies a lot, especially when we deal with batch processing. For instance, applying a function to a list that we divide in batches, and then we just use a pool of tasks. And it allows transparently multiple workers to process tasks concurrently. So what are the differences between process and the pool? Well, the pool is fundamentally higher abstraction than the process itself. We are going to use it because it's automatic process management instead of handling directly the execution of the process by starting, joining. This is automatically taken care by the pool. Here's a simple API. We can do operation in parallel on the dataset by applying a map, apply and start map. We will look at these different methods. Multiprocessing.Pool is the best for batch tasks, also called data parallelism. So we apply the same operation on different parts of dataset that are called batches. And the overhead is lower because the process is automatically, so the runtime systems typically is quite optimized to do this at the lower part of the software stack. So we use processes when we need file control over the execution of the process, but in general, the usage of a pool is preferable because we just need to apply a function to multiple elements efficiently. So this will be much easier and much more expressive, especially we have batch tasks. So let's look at an example of a pool for parallel execution. So in this case, we have a data set that is this array here. You see, we have five elements. We declare what we want to do. We want to apply to each of these elements the square operation. So we define the number of processes that are included in our pool. In this case is 4. And then we defined a multiprocessing pool telling how many processes that we want to have it. And then we need to define which operation we want to apply to the pool of processes. In this case, we're going to call pool.map. We define the name of the function that describes the task and the dataset we want to apply this function in parallel. So the key parts are this one, multiprocessing.pool, that creates a pool of worker processes. See that we're using the with statement here, and this ensures a proper cleanup, automatically close the pool at the end of the last task is done with the execution. The heart of the parallelization is this pool.map, where we define the function with the task and the data set that we are applying. This pool.map applies worker to each element in parallel. Just a brief example we can use for any Monte Carlo technique. And for instance, if we want to calculate the pi, we can use a Monte Carlo technique. What we're going to do, we take a square with each side of size 1, so 0 to 1 and 0 to 1. And then we draw 1/4 of a circle. Take randomly a point in this square, and then we check if it's an internal part, so if this expression is old, where x is the x coordinate of our point, and y is the y coordinate of our point. We check if is 1. So if the point is inside this quarter of a circle, then we add a 1 to the counter. If it's outside, we don't do it. Then, after drawing several points, a million of points, we just take the ratio of the points inside the circle divided by all the points that we check. And then we multiply by 4. This is going to give an approximation of our pi. A simple code to calculate pi using a Monte Carlo technique is the following. So we define first how many points we want to randomly take it. In this case, we take 10 million samples. Then we call our function that is called Monte Carlo pi, given as an argument how many sample that we want to have. Then we have this serial task at the moment that basically is taking x and y using a random distribution, and then is checking if it's inside the 1/4 of the circle. Then we add 1 to our counter, and we do for a number of times that is equal to the number of samples, in this case 10 million samples. And then it returns the number of samples that are within the 1/4 of a circle. Once we have the number of points, we take that number, we divide by the total number of samples, and we multiply by 4, and we will have an estimate of a pi. The larger number of points that we take, the higher precision we are going to have for our pi estimate. So this is the serial implementation. We use only one course. By using the multiprocessing.Pool, we can parallelize quite easily and use all the cores available on your processor. So let's look together at the implementation using the multiprocessing.Pool. So there are a few key changes. So we divide the work across multiple processes, and each worker is going to run Monte Carlo pi. We're going to use a pool map to distributed workload. So it's going to be the same task, but on a different number of points. This slide presents the implementation and the parallelization of the serial version of Monte Carlo code to calculate pi using the concepts of pool. The key changes are the following. We can divide the work across multiple processes. We use a pool map to distribute the workload and to speed up the execution by running in parallel. So in this case, we're going to still have 10 million samples divided by workers. We're going to divide in 4 workers, so this will be, we're going to give 500,000 of sample for each of the worker. So sample per workers, number of sample divided by the number of workers. And then we want to create a pool. In this case, we create with multiprocessing.Pool, and we tell how many cores or number of workers we have in the pool, available in the pool. Then what we're going to do is just to call the pool dot map that is give as an argument the Monte Carlo pi, that is the task to be executed, and then we provide a list with the samples per workers, so with the number of samples. So the results will be a list with the counter from the task for independent execution of this Monte Carlo pi. So this ensures that we are running in parallel using 4 cores. Then this also ensures that there is synchronization because we use with. Once that these tasks are finished, then we can calculate the pi estimate by subbing up the results in this list divided by the total number of samples and multiplied by 4. There are other operations working on the pool. The first one is apply, that allow us to running a single function in one process, and it blocks execution until the function returns, and is quite useful for running one-off parallel task. So if you need to parallelize a single function call, you might want to use the apply function. Another extension of the simple map operation is the star map. Is similar to map because it allows, similar to map because they allow us to run in parallel, but it allows multi-arguments per function call to be run. So in this case, you see we have different argument. So it's very good if we if you need to use a list of tuples for argument and a function that requires multiple inputs. The last function we can apply to the pool is imap. It's also similar to map, but it returns an iterator instead of a full list. So it's useful when working with a large data set. So it saves quite a lot of memory. So these process items as soon as they're ready, instead of waiting for L to finish. In summary, the multiprocessing.Pool class automates parallel execution. The main method is called pool.map that applies a function in parallel, simplified multiprocessing handling. Also we saw apply, star map, and imap that provide additional flexibility. So depending on what is your case, you might want to choose one of the other. This is the last slides of this lecture, and talk to you soon.